Everyone, in this video we're going to talk about compound interest. So our compound interest formula we see right here, and notice it's very similar to our exponential growth equation, but we have n in here, this variable n, right? So if we look down here, we see what n stands for. It's the number of times interest is compounded per year. So this could be compounded monthly, it could be compounded semi-annually, it could be compounded quarterly, right? There's different options there, okay? If perhaps the interest is only compounded once per year, then basically this equation just becomes our exponential growth equation because we would substitute 1 in for n. So it would just become p times 1 plus r quantity and then raised to the t power, which is just our exponential growth equation. So let's look at what these variables stand for. We've already talked about n. P is our principal amount, which is the initial investment amount. I say investment because typically with compound interest, we're talking about money. R is our annual interest rate, same as before, that's represented as a decimal. T is still time in years, and like we mentioned earlier, N is the number of times interest is compounded per year. Okay, so let's look at a couple examples. Start off with a savings account example. We're depositing $500 in a savings account that earns 5% annual interest compounded monthly. We want to write a function that represents the balance after t years, and then want to find out how much money will be in our account after 10 years. So we think to our equation, we say y equals the principal amount times 1 plus r divided by n raised to the n t power. And we're just going to plug in some information. So 500 is going to be our principal amount. So y equals 500 times 1 plus 5% is our interest rate. We're going to put that in as a decimal. And compounded monthly, so that would be 12. There's 12 months in a year. So we're going to say divide by 12, and then our exponent is going to be to the 12t, right? T is still going to stay as t for this first part because we're just writing our general equation for t years. Okay, so now we can solve this a little bit. We're going to say y equals 500 and then 1 plus. In our calculator, we can do 0.05 divided by 12, and we're going to round that and say 0.004 to the 12t. Now we can add in the parentheses and we get the final equation of y equals 500 times 1.004 to the 12t. Okay, and so that would be our equation for t years. Now the next part says how much money is going to be on our account after 10 years. So basically we just take this same equation, but now we substitute 10 in for t and we solve it. So we say y equals 500 times 1.004 times, or raised to the 12 times 10 power. So that's going to give us y equals 500 times 1.004 raised to the 120th power. So now in our calculator we can do 1.004, raise it to the 120 power, hit enter, and then hit times 500. And that's going to give us a balance of approximately $807.26 after 10 years. Okay? All right, let's look at another one where we have a table. It says this table shows the balance of a money market account over time. Write a function that represents the balance after t years. Okay, so when we think about this one, we need to look at the balance that we have, which is on the y value here. We notice that it doesn't tell us anything about compounded monthly or anything like that, so we're going to assume, and notice we just have the years here, year 0, 1, 2, 3, 4, 5, that our interest is only compounded once per year, okay? So essentially we're going to be using our just exponential growth equation. So y equals p, so I know our exponential growth equation, we had an a in there, but since we're talking about an investment account, we're going to use the word principal, right? That's our initial investment amount. So we're going to say y equals p times 1 plus r and raise it to the t power, okay? Now, in order for us to figure out what our R value is, our rate that we're growing by here, we have to look at our balance, right? How is our balance changing? Okay, so we know that when we go from 400 to 436, we're multiplying by our growth factor. Okay, so we can go ahead and fill in our principal amount, which is 400. And now let's think about what we can do to go from 400 to 436, 436 to 475.24, all of those things. So what we can see is, or what we can do is work backwards, right? So I could take 436 and I can divide it by 400, and I'm going to get 1.09. So now that is my growth factor, 1.09. And we can check that, right? So if I said $615.45, and I divide that by $564.63, once again, I get 1.09, right? So my difference here, or my factor that we're increasing by, which makes this an exponential function, is 1.09. Okay, so now we have our equation here, y equals 400 times 1.09. And we could look once again at our growth factor and say, hey, this is a 9% growth, right? Because that's 1.09, and we think 1 plus r. So what did we add to 1 to get 1.09? We added 0.09. So we write that as a percent, and we get 9%. Okay. All right, now, the two examples we looked at so far, we've had growth, right? We're compounding, we're gaining money, that's awesome. We're in our money market account, we're growing by 9% each year. But we know everything in life doesn't always appreciate, right? Sometimes we have assets that depreciate, and one of the most common assets that depreciates is a vehicle, right? So we all, maybe at some point in our lives we'll buy a car, and we know that as soon as you buy the car, that is the most the car is ever going to be worth, right? I know there are exceptions for vintage vehicles and things like that, but for the most part, as you use your car, it's going to depreciate or go down in value. So we can use our exponential decay function to help represent the value of the car after a certain amount of time. So we look at this equation, and it says the value of a car is $25,000. It loses 15% of its value every year. We want to write a function that represents the value y of the car after t years, and we want to find the approximate monthly percent decrease in value, and then we want to estimate the value of the car after 6 years. So we're going to take our equation, and we're going to say y equals, and we're going to say a, and you could use p, I guess, if you want for principal, but now here we're talking about more of a price for something. We're going to say 1 minus r, and we're going to raise it to the t power. Minus, because we're talking about going down in value. So now we're going to plug in our information. So 25,000 is our starting value. And we're going to say 1 minus. Okay, now we have 15%, so we want to write that as a decimal. So we're going to say 0.15, and we're going to raise that to the power of t. Now we can subtract there, and we get y equals 25,000 times 0.85 to the t power. Okay, and so now that's going to be our equation. That represents the value of the car after t years. So now they want us to find the approximate monthly percent decrease in value. Okay, so let's take our same equation, 25,000 times 0.85 to the t power. Monthly means we want to separate that into 12 equal parts. Okay, so we're going to say y equals 25,000, fix that there, times 0.85, and now we want to change basically t to 12t, but we can't change the value of the exponent of t, so now we need to add in an exponent of 1 over 12, and then we can add in 12t, right? Because if I multiply those two together, I'm going to get 12t over 12, which is just t. Okay, so now we've talked about properties of exponents. There is an exponent rule, or a property that allows us to do this, right? I call it power product. You can check that out in the top right-hand corner if you want right now. But now what we can do, basically, if we're multiplying these two exponents together, that means we could separate them. So I could plug in, I could say y equals 25,000 times 0.85, and now I can put the exponent of 1 over 12 on the inside with 0.85, and we can raise it to the 12t. Okay, because if we saw this part right here, then we know, hey, we can multiply those two exponents, right? Power product. Now we can use our calculator, and we can type in, so we can write down y equals 25,000, but now we can type in 0.85, and we can raise it to 0.85, and we can raise it to the power of 1/12. Okay, that's going to give us 0.986. So we're going to say 987 to the 12t. Okay, so now that gives us our decay factor. So now to think about our decay factor, right, that's this part right here. This was 1 minus r, and now it's equal to, or approximately equal to, 0.987. So what did we subtract from 1 to get 0.987? Well, we could say R is equal to 0.13, okay? And so now, actually we're gonna say 0.013. And now we want to change that to a percentage. So we're going to say move the decimal twice to the right. So our percent decrease, right? Let's say monthly percent decrease is 1.3%. Okay. All right, last part, estimate the value of the car after 6 years. Okay, we're going to go back to our equation that we found on part A, and we're just going to plug in 6 for t. So we're going to say y equals 25,000 times 0.85 raised to the 6th power. So we say 0.85 to the 6th, and we multiply that by 25,000. Okay, and we're going to get approximately y equals $9,428.74. So that would be the value of the car after 6 years, right? So you can see we started at 25,000, only 6 years later, we're less than $10,000 in value. So that's definitely an example of exponential decay, and we call that in real life depreciation, all right? So there's a little bit about compound interest.